All right, we've been talking about heat versus temperature, and then we talked about thermal expansion and contraction and how different substances expand or contract based on a increase in the energy due to thermal transfer. So now I want to talk about an aspect of energy transfer that we call specific heat. Now, specific heat or heat capacity is the ability of a substance to absorb energy in the form of heat, and different substances have different amounts of specific heat. When you see this term specific, all right, the word specific generally means per amount. So because our base unit of amount in physics is kilograms, we basically are looking at per kilogram. All right. So the specific heat is how much a substance can absorb energy before it changes temperature. And this is a unique property for every substance. Every substance has its own specific heat, so we can use that to identify a substance if we know how much energy has been transferred to or from it and how much the temperature change has occurred. It's something that we can use for different purposes and use specific substances to accomplish different tasks, to absorb more energy or to release more energy. For example, if we store energy in the form of heat, because it's unique, we can use that then and do some quantitative analysis of that to figure out the amount of energy that each substance needs. But it's based on how much of that substance we have. We saw the hot tub versus the Atlantic Ocean the other day in our slide, and the hot tub was 102 degrees Celsius, the Atlantic Ocean was 56 degrees Celsius or whatever, or I'm sorry, degrees Fahrenheit. And the difference in the amount of energy in the two of them was vastly different because the Pacific or the Atlantic Ocean is that much bigger. But they both are based on water. So the amount of energy per molecule of water was higher on average in the hot tub, but the amount of energy to warm up the water is the same per kilogram of water. All right. So the specific heat depends on the interaction of the molecules in the substance. We're not going to get into the details about that, but it's energy that can be stored in the bonds of the molecules or atoms of the substance. It's the intermolecular forces that hold the atoms or molecules into the rigid structure of a solid, or hold them together as a liquid, or release them as a gas. So it depends on the type of substance, and it depends on the state of matter, solid, liquid, gas. So for example, water has a different specific heat when it's in liquid form than it does when it's ice. And it has a different specific heat as steam than it does as water, as liquid. So each substance has 3 different specific heats based on what phase of matter it is as well. The higher the specific heat, the more energy it can absorb before it changes temperature upward, or the more energy it can release before it changes temperature downward. So it's basically how much energy per degree Kelvin or degree Celsius per kilogram. So if I have a kilogram of water versus a kilogram of iron versus a kilogram of ice versus a kilogram of aluminum, each of those is going to absorb heat differently. And that heat is absorbed in the substance and stored somehow in the molecular motion of that substance and the attractive forces of the molecules and atoms in that substance. And depending on the structure of that substance, different substances have better ability to store energy than others. All right. And our unit that we use is joules per kilogram per Kelvin. So joules per kilogram Kelvin is probably the best way to say it. You can say joules per kilogram degrees Celsius as well. So that means if I have a kilogram of substance, how many joules to raise it 1 degree Celsius. And the more joules to raise it 1 degree Celsius, the higher the specific heat. So here's some examples of specific heat. We can see here, and we assume that these are substances at room temperature, so they're in their natural form at room temperature, so aluminum, brass, carbon, copper, glass. Ice obviously is not at room temperature, so these are all solids on the left-hand side. Water obviously is not at room temperature, and water vapor is not at room temperature, but you can see there's different specific heats. And water is pretty unique because it has a very, very high specific heat. 4,180 joules are needed to raise 1 kilogram of water 1 degree Celsius. While lead, if I have a kilogram of lead, it doesn't take up as much space because it's much more dense, but it only takes 130 joules to raise that 1 kilogram of lead 1 degree Celsius. So it's got a very low specific heat when compared to water. In fact, it's the lowest specific heat on this whole chart. But what that tells us then is that if we have a substance at a certain temperature, how much energy would it lose for every degree Celsius or every Kelvin that it drops? So we can quantify the energy in relation to the temperature. So what specific heat does is allow us to connect energy and temperature. Energy in the form of heat, which we measure in joules, and temperature in the form of degrees Celsius or Kelvin. And we've got these different comparisons. Water tends to have a very high specific heat compared to most other substances, and that's what makes water unique. One of the things that allows our Earth to have as narrow a zone of temperature as we do compared to other planets is the amount of water on the surface. And the water can absorb a lot of energy before it changes temperature. So it maintains a much narrower range of temperature on the surface of the Earth and much more livable temperatures for animals and other biological objects to exist. So that's a huge aspect of why we look for water in space exploration, why we look at Mars and see, is there existence of water or evidence of the existence of water? Because if there is, that means that the temperature of that planet can be regulated better. This is our formula for specific heat. You probably saw this last year. Last year in chemistry, we call it MCAT because the delta here looks like a that just means change in temperature. Delta T is change in temperature. The capital T is generally regarding kelvins, absolute temperature, but since a change in temperature is what we're looking at, you can use kelvins or degrees Celsius because 1 degree Celsius is the same as 1 Kelvin. So we have here the energy gained or lost in joules. So Q is the amount of energy gained or lost. So if it's gained, it heats up. And if it's lost, it cools down. So the sign of Q tells us whether something has increased in internal energy or decreased in internal energy. Delta T is the temperature change, and that can be in Kelvin or degrees Celsius because they are the same in terms of change. Mass is simply kilograms. A kilogram is a substance. And C is what we call a specific heat. That's a numerical value that we saw that's specific to each substance and the phase of that substance. So water, for example, is 4,180 joules per kilogram degrees Celsius, or joules per kilogram Kelvin. Okay, so each of those quantities are measurable and findable. So oftentimes what we do is try to solve for how much energy it takes to change the temperature of something. To do that, we need to know how much of that substance there is and what its specific heat is. So we have tables of specific heat like we saw in the last slide. So let me show you a couple examples here. All right, here's a table of specific heat, and the same table as what we had in slide 2 and a typical couple questions. How much does the temperature of a 500 gram mass of silver change if it loses 10 kilojoules of internal energy? Now, 500 grams is 0.5 kilograms. So that's our mass. And this loses 10 kilojoules. Well, kilojoules is thousands of joules. So Q is negative 10,000 joules. All right. Well, we have Q equals MC delta T. If delta T is negative, Q is negative, right? If delta T is positive, Q is positive because mass and specific heat are always positive. In this case, the temperature of the silver will go down because it's losing 10,000 kilojoules of energy. So we know M, we know Q, which is silver, which is right here, 235 joules per kilogram degrees Celsius. And we know the amount of energy change, Q. So the only thing we don't know is delta T. So we can rearrange that to solve for delta T, and we get 10,000 divided by 0.5 divided by 235 joules per kilogram Kelvin. So our answer here is 85.1 Kelvin, and that should be negative, all right? Because it's a loss of 10,000 joules. So we screwed that up in our notes here. So it loses 10,000 joules, so it loses 85.1 kelvins, or 85.1 degrees Celsius, you could say as well. Okay, the second question, you have 20 kilograms of lead. Now, lead has a very low specific heat, 130 joules per kilogram Kelvin, and 10 kilograms of zinc. Zinc has a higher specific heat, right here, 388 joules per kilogram degree Kelvin. So if we want to warm them both up the same amount of temperature, 22 kelvins, and then we have the same, we have twice the amount of lead as we do zinc, we have to look at Q equals MC delta T and see how those compare. The M is twice as much of the lead, but the C, remember this is a C, is less than twice. 130 is less than twice of 388. So what we're looking at then, since we have double the mass of lead, but its specific heat is about a third of it, it's going to take more energy to warm up the zinc, the same amount of temperature. So delta T in this case, if you wanted to do the calculations, delta T would be 22. Q would be what you'd be solving for. And M is the mass of each of the substances, and you'd have to put in the C for lead and the C for zinc for those different masses, and you'd find that Q is greater to increase the zinc's temperature. All right. So here's a question I want to leave you guys with. So I'm going to start with this question when we get back to each other. Which group is in more danger of hypothermia? All right, think about what they're doing. The guys on the left, I believe it's Chinese police force, is showing their macho-ness by putting ice or snow on their torsos, while the other people are showing their macho-ness by jumping into probably Lake Michigan with the ice and stuff there. So think about the temperature of the water, think about the temperature of the air, and what's going on with that. Hypothermia is a dangerous drop in body temperature. Where are they going to have a more possibility of losing body temperature? In contact with the air or in contact with the water? All right. So we'll try to pick up with that as we get back. We're going to use specific heat quantitatively to compare the amount of heat gained by one substance to the amount of heat it gives to another substance and how their temperatures differ. So we'll also have a little demo that we're going to show you guys dealing with this. All right, have a great day.